Hello everyone. I welcome you all to the second video of this series where we are trying to build a machine learning model for a chemical sciences problem. Just a quick recap about the last video. We have this data in the Delaney_CSV file where we had the smile strings of the molecules and their Maillard log of solubilities. And what we are trying to do here is we are trying to predict the solubilities of these molecules based on the descriptors. And since we had just the smile strings, we went ahead and generated molecular descriptors using Mode-RED library. Initially, we had 1826 descriptors, and we did some data processing where we removed strings or errors from our data sets, and then we went ahead to remove constant values, and finally we removed highly correlated variables. And in the end, we had a data set with 281 descriptors, and we stored that in Delaney_Mode-RED_truncated.csv file. So in this video, we will see how we can build machine learning models using this data set. So what I'm gonna do here is first I'm gonna import pandas, numpy, and other libraries in here. We don't really need RDKit and Mode-RED, so I'm not importing these. But we are going to be needing pandas and numpy for data manipulation, seaborn matplotlib for plotting our data. Just to give a good look to our plots, I'm using a wide grid style of SNS. Okay, so once we have imported all these libraries, let's just go to our building machine learning model section, and also we are going to be importing libraries as we move along. Now, okay, this is the file in which we had our data. So let's just go ahead and load this data set and have a look at our first 5 data points. So this is our kind of truncated data set. We had names of the molecules, their smile strings, Maillard log of solubilities, which is our target and which we want to predict based on all these 281 descriptors. So let me just again print out the shape of this data set. So we have 1144 data points and 281 descriptors if we take these 3 columns out. So the first step is defining our dependent and independent variable. So this is gonna be our dependent variable or target. So I am gonna be storing this in a variable called y, and I am just gonna slice this data set based on this column. So let's go ahead and run this. And if you wanna see, y is just a pandas series having these values. Next, our independent variables are all these 281 descriptors. Now, what I am doing here is I am scaling my data set using standard scaler. If we look at the official website of sklearn, standard scaler is a class which helps us in standardizing the data set by removing the mean and scaling to unit variance. And it is highly recommended and a common requirement for many machine learning estimators, as they might behave badly if the individual features do not more or less look like standard normally distributed data. So basically we want the data to be normally distributed, and as a result we are running this standard scaler. So what we are gonna do is we are just gonna import this class standard scaler from sklearn.preprocessing module. So let me just uncomment this and run it. So we have imported standard scaler class, and next what we are gonna do is we are just gonna scale this using standard scaler. So let me break down this code for you. So our data set is in column index number 3 and above. So this is 0, 1, 2 and 3. So first step is just slicing this data set. So I'm using iloc, and we want all the rows, and colon would do that job for us, and we want all the columns including and beyond 3 index. So let's see this. So we have all the descriptors in here, and we have gotten rid of these names, smiles, and our target. So next what we wanna do is we wanna use a standard scaler class and call a fit transform method on it. So standard scaler is a class that we just imported, and fit transfer Transform is a method that we are going to be using for scaling this data. So I am just cutting it from here and pasting it above here, so it will scale all these columns here. Now let's just run this again. So we have got the data in the form of numpy arrays. So if you wanna see the type here, it's a numpy array, but we want the data in a data frame. So what I'm gonna do is I'm gonna use pd.dataframe, which would convert these numpy arrays into data frame. Here we have a data frame, but the column names are missing. So what we can do is just use columns from our initial data set, which was df underscore final, and of course we need to grab the descriptors column, all the rows and columns including and after 3 index. So now we have the data set in here with all the names of the descriptors. So we can store this as scaled df. So that is what I have done here. We can just get rid of this. Okay, so we have the scaled data now, and we don't really need to scale our target. You can do that, but it's not really necessary. And now we are gonna split this data set into training and test set. In order to split our data set into train and test, what we need is we need this train underscore test underscore split method from sklearn.model underscore selection. So let's just go ahead and import this method. So in here I'm gonna be importing train test split. Okay, so now it will take in argument as our scale data set and our target. So we also need to put in how much test size we want. So 0.20 basically means out of all the data points, 20% would be our test set. So basically if we had 1144 data points in total, 20% of it would be our test samples. And random state I am giving 45 just for the sake of reproducibility. Otherwise every time you run it will give you a different train and test sets, and as a result your results can vary. So just for the sake of reproducibility I am putting a random state of 45. So let's just run this. So it has been successfully run. So I'm gonna be looking at the size of our X train. It's capital. So we have 915 data samples in X train, and regarding X test we have 229 samples. You can increase and decrease your test size at your will. You can put it to 30% or 35% or even 15%. That's totally up to you. Now next step is building our model. So one thing you need to remember is that according to Occam Razor, the simplest explanation is usually the best one. So we must start with the simplest model, for example linear regression model. And if that model works well for our data set, we don't really need to use advanced algorithm. So what I'm gonna do is I'm gonna be using stats model, and I wanna show you how you can build a linear regression or a multiple linear regression model using stats model. So for that we have to import statsmodel.api as sm. Now I have already talked about multiple linear regression and linear regression in depth in my previous videos. So if you haven't checked those out, I highly recommend you to check out those videos. I will provide you the link in the description below. And so what we are doing here is we are adding a constant to the intercept here, and the variable is x train. And in the next step we are using this OLS, which would take in argument as y train and x, which is basically our training data, and we will fit using this fit method, and the results can be displayed using this summary method here. So let's just run this and see the results. Now, since we are using 281 descriptors, you can see we have, the coefficients for all of these descriptors in a tabular manner. So let's just first start with R square. So R square is pretty good for our training data, 0.953. Adjusted R square is 0.933, which is little less than R squared, but this is not really the concerning thing here. The main point you must note here is that not all these descriptors are relevant for this linear regression study here, and I have already made a point in my previous videos that we need to have a look at the p-values, and if the p-value is less than 0.05, then that means that descriptor is irrelevant, otherwise it's not. And we can very well see here that all these descriptors ABC and base, SP-MAD, all these have values above 0.05, so they are basically non-relevant descriptors. VR1 is seems good here. It has a value of less than 0.05, but again N atom and all these descriptors have p-values more than 0.05, so basically these are irrelevant descriptors according to OLS, which is ordinary least square method we are using to fit the line. Now that brings me to another topic of curse of dimensionality. Basically, these machine learning models suffer from this curse of dimensionality, which refers to various problems and challenges that arise when dealing with high dimensional data. As the number of features or dimensions in a dataset increases, the amount of data needed to generalize accurately also increases exponentially. Now, what are the problems that is caused by this curse of dimensionality? The first one is sparsity of data. The ratio of data points relative to the number of descriptors decreases. This sparsity can make it difficult to obtain reliable statistical estimates and may result in overfitting. It can lead to increased computational complexity. With increase in dimensions, the computational resources required for processing the data also increases. Algorithm becomes computationally expensive, and the time complexity of many algorithms can become prohibitive. Last but not the least, it can lead to model overfitting. With a high number of dimensions, there is a risk of models capturing noise in the data rather than genuine patterns. This can lead to overfitting, where a model performs well on training data but fails to generalize to a new unseen data. And we are gonna see that in a bit by fitting the test data to our model, and that would kind of give us an idea whether this model is overfitting or not. So let's just go back. So I'm just gonna comment this one out, and now we are gonna be looking at scikit-learn for building this model. So again, I'm gonna be importing this linear regression class from sklearn.linear_model. Now it's very simple. We just need to create an instance of this class, and I'm storing this in a variable called LR, and then we just need to call a fit method with xtrain and ytrain as a variables. So let's run this. So we have successfully fitted our training data into this linear regression model, and now we are gonna be analyzing some of the results. So the very first thing we need to analyze is our square values. There are many ways which you can do that. What I am doing here is I am using this score method on this LR, and the variables that I'm putting is xtrain and ytrain in order to get the R square score for the train set. And for the test set, I'm using xtest and ytest instead of xtrain and ytrain. So let's run both of these commands and see. So our square for the training is 0.95, and for the test it's 0.62. So basically that means our model is overfitting. And overfitting is a common problem in machine learning, where a model learns the training data too well, capturing noise or random fluctuation in the data rather than the underlying patterns. This phenomenon occurs when a model is too complex relative to the simplicity of the underlying true relationship in the data. And we have already seen that in our model we have used so many descriptors, and most of these descriptors are probably irrelevant, as a result of which we are seeing overfitting in our data. So for linear regression in particular, or multiple linear regression in particular, the way it's done is you just cherry pick your descriptors, and each time You add a descriptor iteratively, and with each addition you check your R square and p values, and if R square is increasing and the p value is relevant, then you just stick to your descriptor, otherwise you just remove it. And that's a tedious process, but there are other techniques as well, such as dimensionality reduction, which I'm gonna be talking about in this series of videos. Another thing you can do is you can use a different model. For example, here I'm using random forest model for predictions. Now before I talk about random forest regressor, I just want to quickly talk about one more method by which you can calculate R square, and it's really important. Now what we can do is we can call a predict method on LR, and we can calculate the predicted solubilities, right? So this y hat train is the predicted solubilities using this training data, and y hat test would be the predicted solubilities of this test data. Now what we have to do is we have to just use this predict method, which would take in argument as x train for predicting the solubilities of training data, and as x test for predicting the solubilities of test data. So let's just run this, and we can see that y hat test has a size of 229, which is equal to the test size, and for the train we have 915 values. So it's one-dimensional array. Now what we can do is we can use R2 score method from sklearn.metrics. So I have imported R2 score again along with the mean absolute error, and all we have to do is in here just use R2 score and put in variables as y true or y train and y predicted, which is our y hat for the training set. So it should give us the same result as this one, 0.952. So let's run this and see. So you can see we have the similar result with a different method. And again, if you want to see the accuracy of our test set, all we have to do is replace train with test, and it is similar to our test accuracy that we have calculated before. Now let's talk about random forest regressor. So this random forest regressor class belongs to sklearn.ensemble module, and it is a meta estimator that fits a number of decision tree regressors on various subsamples of the dataset and uses averaging to improve the predictive accuracy and control overfitting. I highly recommend you to visit the official documentation of sklearn, as they have pretty good documentation of pretty much everything what they have in here. And so let's just go back, and in here what I'm gonna do is I'm gonna be importing random forest regressor class from sklearn. Now in here all we have to do is, like linear regression, create an instance of this random forest class and then call a fit method using xtrain and ytrain, and that would train the model using these data points. So we have fitted our data, and let's just have a look at the score. So I'm just what I've done is just copied and pasted it over here and replace this LR with RF, which is our estimator. So let's run this. So in here you can see we have a pretty good training accuracy of 0.98, and our accuracy for test set is also pretty good, 0.86. Although there is some overfitting, as you can see there is a difference between these scores here, so we do see some overfitting. Again, the reason is that there are so many descriptors and not all the descriptors are useful, and I'm gonna be talking in detail about how you can reduce the number of these descriptors in my coming video, so just stay tuned for that. Okay, so we have built our models. Again, you can go ahead and try other models as well. There are many other models out there which you can try. There is one way you can do it manually, but there is another way using a package called Lazy Predict, which I'm going to be talking about in a minute, in which you can just screen more than 40 models just in one go in just few lines of code. So just stay tuned for that. I'm going to be showing you that. But before that, I want to talk about cross validation, which is a very important topic. Now in here we have just randomly split our data, right? In here it's just a random split, and we want to make sure that this is not just out of fluke that we are getting such good results. And for that we need to cross validate our results. And in here what we need is we need to import this cross val score method from this sklearn.model underscore selection. So let's run this, and in here we need to put in our estimator and our training data, both xtrain and ytrain. I'm using R2 as a scoring method, and this CV is equal to 5. Basically we wanna do 5-fold cross validation. And let me just give you a brief description of what this 5-fold cross validation means. So we have this training data, right, which had 915 data points. So what we are gonna do in cross validation or 5-fold cross validation is we are gonna split this data set into 5 equal sets, and each set would be having 183 data points, right? 183 into 5 is basically 915. So okay, we have these 5 sets. So what we are gonna do next is we are gonna, in the first iteration, use these first 4 sets for training and use the 5th set for testing purpose. So we are gonna be having a score, an R2 score for this particular iteration. And in the second iteration, what we are gonna do is we are gonna be using this first, second, third, and 5th set for training, and the 4th one for test. And again, we are gonna be having a second R2 score. In the third iteration, 1, 2, 4, 5 as training, third one for test. We have the R2 now. And in the fourth, 1, 3, 4, 5 as training, second for test, and we are gonna be having 4th R2 score. And in the 5th iteration and final iteration, we are gonna be using first set as test set and second, third, fourth, 5th as training set. So in the end we are gonna be having 5 R2 scores. So that is the purpose of this line of code here. We are using cross underscore val underscore score function, which would take in our training data, use random forest estimator, and it will use R2 scoring and cross validate 5 times, basically 5-fold cross validation. You can have 3, you can have 10, you can have 7, or whatever. I'm just using 5 here. So let's run this. It'll take a little while. So finally it has finished running, and our results are stored in val variable. So let's see what this val variable has. So we have an array of 5 points, and all these are R2 scores of each iteration. First one is 0.89, second one is 0.87, and so on. And these values are pretty consistent, and they are quite high, around 0.90. So I think we have a good data set here. And what we can do is we can just take a mean, and that would constitute a mean cross validated score, and that's what we can report in our project or publication or whatever. In case it's less, let's say 0.40 or 0.50 or even 0.60, and our training and test is around 0.90, that means we have a problem. So make sure you cross validate your results before you reach at any conclusion. So this was all about cross validation. Next I wanna talk about visualizing the results. So first what I'm gonna do is I'm gonna plot a scatter plot between measured log of solubilities or actual solubilities and our predicted solubility. So for predictions, what I'm gonna do here is use predict method on our X test using random forest estimator. Again, if you use linear regression estimator, that will give you a different scatter plot because we will have different predicted values. So in here I'm just using random forest, and let's just run this first. And I'm also gonna label our X and Y axis. So this is the scatter plot between measured solubilities on our x-axis and predicted solubilities on our y-axis. So it has a pretty good correlation here. Now next what we want is we want to plot a regression line between measured solubilities in the training data to the predicted solubilities in the training data. So again, for predictions, I'm using predict method on X train, which would give us Y hat train, and I'm giving a different color, maroon, so that we can distinguish train and test points. And alpha is 0.3. This is for transparency. Basically, I want to make the train values transparent so that we can see what's behind those. And again, these are all labeling. So let's just plot this. Okay, so we have the final regression line here and the train data as well here. So in this way, you can plot a regression plot between your predicted and measured values. Next I want to talk about is lazy predict package, like I promised, to screen all different kinds of models in just few lines of code. So first, all we have to do is install this lazy predict package. Now after it has been successfully installed, we are gonna be importing this lazy regressor method from our class from this lazy predict underscore supervised, and then create an instance of this class, and followed by using fit method, and in here we put in our x train, x test, and y train and y test. So all of our data with partitioning into training and test set goes in here, and it will save the predictions in this predictions variable. So let's run this, and you can see the progress here. So it has finished running the code, and we have the results here. So this is the R squared here, and as we go down, the R squared increases. So these Bayesian ridge and elastic net has given us the maximum R square value of 0.91. Lasso CV and Lasso Lars CV, they are pretty good as well. Extra T regressor and Lasso Lars IC, both the four of these have 0.90. And if we look at our random forest, now these are the R squared values for test set. So let's just compare the R square values for our models which we have used, random forest and linear regressor. So let me find them here. Okay, so random forest regressor has a value of 0.86 here, and linear regression has R square value of 0.62. So let's go up there and see if it matches with our predictions. So in here, for random forest, for linear regression, yeah, it is 0.62 here for the test set, and for random forest it's around the same, 0.866. Okay, so what we can do here is we can just grab, I think it does not really matter, you can just grab any of these, I think above 0.86 or above 0.87, whichever algorithms are easy to run or have a more opportunity for hyperparameter tuning, you can just grab any of these here and just go with hyperparameter tuning, and I'm gonna be talking about that in our coming videos. So this is how you can screen all these models in just one go and shortlist just few models for taking them forward. So I think I'm gonna end this talk right here, and if you're interested in these kind of videos, make sure to subscribe, and I will see you in the next video. Thank you for watching.